Good afternoon. Welcome to Krishna's class. Let us continue with our exploration of the Lebesgue measure on RK. What have we done so far? So far, we had X taken as RK, a locally compact Hausdorff space, which is also sigma compact for K equal to 1, 2, 3, etc. Now, these are the basic properties of this. It's a locally compact Hausdorff space and it is sigma compact. Now, for f belonging to CCRK, we defined lambda f to be the limit n tends to infinity of lambda nf, where lambda nf was given by 2 to the power minus nk sigma summation over pn fx. That means the value of x at every point in Pn. Pn consists of points in Rk whose coordinates are of the type m1 by 2 to the power n, m2 by 2 to the power n, etc., mk by 2 to the power n, where all the mi's are integers, positive and negative. Then lambda is a positive linear functional, and one can apply the Rees representation theorem. And by Rees representation theorem, there exists a sigma algebra, script m, and a measure m such that this is RKMM is a measure space. Now, what we are exploring is the properties of this space, and this happens to be the so-called Lebesgue measure space. Now, in particular, for k equal to 1, this gives RMM, gives the Lebesgue measure, which we have developed with a lot of effort all along. Okay, now we have to prove that M is a Lebesgue measure on RK, which is having the property that it's a complete measure, it's a regular measure, and it is translation invariant. Now, these are the primary properties of the Lebesgue measure. The Lebesgue measure has the property that, and of course, all the boxes in RK have their measure given by their volume. Now, for n equal to 1, this corresponds to, the basic properties of the Lebesgue measure. What does it say? For intervals, it is the length of the interval. Now, that is the analogous property is given by that the boxes have their measure given by their volume. Okay, that we will write below clearly. The second property is that you have, if you translate a subset, a measurable subset of the real line through to the left or to the right, see, the resulting set is also having the same measure. That means this translation, the measure is a translation invariant function. And the analogous thing here is, if you have E a measurable set and X some element of RK, then E plus X is the translate of E through the vector X. So you get another set which is a measurable set and has the property that the measure of E and the measure of E plus X are the same. Okay. So that is a very crucial property of this. Then there are two other properties which we shall describe, or more general type of results on the, instead of translation, we will be also looking at what happens if you apply a linear transformation to the measurable set. Okay, that we will do towards the end of the proof theorem. Okay, so what have we proved? I mean, we have shown that We have already shown that the measure of W for any K cell W in RK, the measure of W is the volume of. Now that is the one that really fixes the one of the basic properties of the evacuation. Now all Borel sets in RK belong to what are Borel sets? They are all, you have the open sets. That means you are going to integrate the sigma algebra with the topology. So all open sets in RK, right, with the usual topology on RK, are measurable sets. Okay, that's the first thing. The second thing is that, see, you take the arbitrary union, you take the complementation of open sets. What do you get? You get the closed sets. So all closed sets are also belonging to the sigma algebra. Further, you take a countable collection of open sets. If you take the union of them, then you get an open set. So there is nothing to talk about it. But when you take the intersection, this may not be an open set, but nevertheless, such a set is what you call a G delta. That is the intersection of countable intersection of open sets is what you call a G delta. So all G delta sets are also in RK. Similarly, you take closed sets and take their arbitrary or countable union of them. And you take countable union of them, in general it need not be a closed set. Okay. So such sets are called F sigmas. And by the basic property of the sigma algebra, you see that they are also in the sigma algebra. Okay. So all F sigmas and all G deltas are in script M. So you know what F sigma is? And then of course you have the further taking the arbitrary union, countable unions and countable intersections, because they all from the basic property of the measurable sets of the sigma algebra. So all F sigma and D deltas are every Borel set this we have seen. Now further, what more you can say? If E is an element of script M, then there exists A and B where A is a F sigma and B is a G delta such that A is contained in E, contained in B, and B minus A This belongs to M, and measure of so any measurable set can be squeezed between a F sigma and a F sigma and a G delta. Okay, right? And such that their difference V minus A as its measure. See. Now this also you have. This, of course, we didn't have to write a proof for this because we already done the basic theorems on the properties of this. And you see that in this part, it is significant to have RK sigma compact. You know, in the representation theorem, we are not assuming X to be sigma compact, and you don't get this property over there. Okay, but in RK, by the very nature of RK, it's not only a locally compact Hausdorff space, but it's also a sigma compact Hausdorff space. Okay, and this sigma compactness essentially guarantees that this property is satisfied. Okay, so you have the second criteria. This also we have got straight away. Okay. Now what we prove is a crucial property, namely C, measure of that is and X belonging to. So if you take any vector X in RK, fix it, choose some measurable subset or an element of M, and then you take the translate of E through the vector X. Because you are in a vector space, you can translate. Every vector can be translated. What do you mean by translation? Just add this vector to it, and whatever vector you get will be the element. So you will be essentially the analog of moving the subset of R to the right or to the left to some real number by adding it. Okay, so here it is the vector addition that we. So E plus X is equal to this is what you get. Therefore, what you prove is this measure of E plus X is equal to measure of, that is M is translation image. It's a crucial property for the Lebesgue measure. Okay, so let us prove this. So fix proof of C is C. Fix X belonging to R. Define lambda E to be equal to measure of E plus X. Now you see that this is well defined because E is a measurable. E belongs to E plus X is therefore measurable, and M of E plus X is a non-negative real number. Okay, and that you set as the new measure of E. Now what we want to prove is that lambda is equal to small m. This is what we want. Now by A, measure of E plus X lambda of E equal to measure of E for every box, K box So if you are restricting to K boxes, then you see that this property is satisfied. Okay, so now we have to go from the to the power sets. Hence, measure of E plus X equal to measure of E for every boxes and consequently for all oral sets. Now, how do you come across this? Because you take a Borel set. A Borel set is an F sigma or what you. Okay, then first we will get it for open sets, because open sets can be written as the disjoint union of boxes. Okay, therefore you get the measure for open sets, and from open sets you can get it for closed sets, and from there you can get it for all Borel sets, because you know how Borel sets are generated. Okay. That is the smallest sigma algebra that contains all open sets. Okay. Now, if E belongs to M, there exists A and E and B subsets of R. A is A F sigma and B is a G delta. That means countable union of open sets, and this is countable union of closed sets, and this is countable intersection of open sets, such that they are obviously measurable. Which implies, you see, the measure of E is equal to the measure of A. That means you can approximate E from inside through what are called closed sets, and from outside through open sets. Okay, and this is what you get. Hence, we have so that proves the particular claim. Okay, that means M is translation. What next? So D will go. Now you are talking about any other positive translation invariant measure on RK, then that translation invariant measure is a multiple of the Lebesgue measure. So in some sense, the Lebesgue measure is uniquely determined. So it's only up to a scaling factor. This is what it means. Okay. So let mu be any positive translation invariant measure on R. Such that the measure of compact set, mu of every compact set is left. Then what we can claim is this: there exists a constant naturally positive constant C, or a non-negative constant C, such that in fact it is a positive constant. So let me write that. C greater than 0, such that mu of E Okay. Let us work out this. How do we prove this? So we go to the proof of this. Let Q naught a 1 box. 1 box means what? Okay. A 1 box means that is Q naught is the union of to the power nk disjoint to the power minus n boxes which are this is what you have. Suppose in R2 you have a box whose edge has length 1. Okay, all this Q naught. With of course the corners be having coordinates which are integral multiples of are just integers. Now what can you say about this? Now then what we are doing is we are subdividing this actually. Subdividing and so on, subdividing and so on. So eventually you see that you can keep on subdividing until you can write it as the union of 2 to the power nk disjoint 2 to the power minus n boxes which are translates of one another. Okay, right? So you have to actually subdivide this until you get the edge of the smaller box that is inside is of 2 to the power minus n. Okay, and then you will see that when we are working with k equal to 2, so you see that 2 to the power 2k that you have, then you have this disjoint 2 to the power minus n boxes which are translates of one another. So this is the union of such boxes. Okay, right. Now what do you get? Then what you observe is that the important point is that each box is a translate of any other. If you take this, translate it. You take this, translate it here. Take translate here. So any one of them is a translate of the other. So all of them have equal volume. Okay. Therefore, same volume and we already used 2 results about the volume, the measure of the box, and the other one is this M is translation variant. Okay, therefore what do you get? Two to the power minus 2 to the power nk mu q. Q is a typical box here, mu q equal to, each of them have the same measure, so this is equal to mu of q. And this is equal to C of m of q naught. That's a relation between them. And this is equal to C times 2 to the power minus nk in the measure of q. Some q naught is that. And what is that? This implies mu of q equal to C times. So we are using the fact that mu q naught so this is the result that you get. Mu of q equal to C times mq. This is true for every one of the 2 to the power minus n boxes. So this property is satisfied. Now every open set in RK is a countable union of disjoint boxes. This we have proved. Boxes belonging to omega 1 union omega 2. This we have proved earlier. And therefore, and for each one of these boxes, this particular property is satisfied, and this is a disjoint union. Therefore, you get this equality true for every. Hence, mu of E equal to C of M of E. Consequently, mu of E equal to now it is quite easy to prove for every. Okay, so what happens is the importance of this theorem is that every other measure having the basic properties of the Lebesgue measure is only a scalar multiple of the Lebesgue measure. Okay, so in some sense, up to a scalar multiple, the positive scalar multiple, the Lebesgue measure is uniquely current. That is the consequence of that. Up to a positive scalar to a positive multiple, the Lebesgue measure is uniquely determined. That means we are taking all translation invariant measures, okay, which are eventually equal to having this particular form. Or in short, what you are saying is that it's a scaling factor. Every other Lebesgue type measure is coming out from the basic Lebesgue measure through a scaling factor. So they differ. Two such measures differ only by a scaling. Now we prove this next property. For every t belonging to is a linear transformation on Rk. That means this is from t is from Rk to Rk, which is linear. There corresponds in real number delta t such that measure of the image of E under T is equal to delta T times measure of okay. So this is the next property that this is in a way a generalization of this research. So let that is T is a linear transformation from Rk to then we know that for any t, the range of t is then not just a set but a subspace it need not be the whole of Rk. For instance, if you take projection along one of the coordinate axes, then you see that it's going to get projected to a lower dimensional space. Okay. So we now split this case into two parts. One, dimension of strictly less than k, which is the dimension of the space. You know that Rk is k dimensional. In this case, we take delta t to be 0. into measure of y equal to 0. Now choose therefore for any subset this is also true. Okay. For any subset the image is set of measures 0. So in that case this is true, and consequently you get this result that measure of equal to 0, that is so that holds in that case. Now you take the case second, T belongs to is a linear transformation on Rk, which is 1 to 1 and 1 to 1 on Rk. If it is 1 to 1 on Rk, it is also on to, or if it is on to Rk, then it is 1 to 1, either. Okay, that is which implies T is a homeomorph on Rk. It maps all open sets into open sets. Okay, it's 1 to 1, 1 to, and maps all open sets. So it's a homeomorphism. Its inverse is also 1 to 1 and all. Okay. It implies E is a Borel set. Open sets are mapped to open sets, closed sets are mapped into closed sets, and therefore eventually you get open sets or Borel sets are mapped to Borel sets. Now define a positive measure Borel measure by mu of E equal to measure of E. Then mu of E plus X equal to measure of T E plus X, which is by linearity measure of T E plus Tx, and that is the translate of T. Therefore, this is equal to measure of T, measure of T, and that's equal to mu of E. That's how we started originally. Okay. Mu E equal to measure of E. So we get this result. Okay. Thus, mu is translation invariant. So mu inherits the translation invariance property from the definition. Hence, their excess C positive such that non-negative such that mu E equal to C times measure. This is true for every Borel set. No. Okay. And hence, every measurable set. Now, to find delta T, what we do is we compute measure of E for E with not equal to 0, then this is well defined. Okay. Then 0 is, that means with measure of E finite also. Infinity. Okay. In particular, if T is a rotation, it's a linear transformation. Let E be the unit ball then what do you get? T is a rotation. So T of T is then equal to, hence measure of equal to Measure of t is measure of is equal to, that is delta t is equal to this is in the case if t is a rotation, rotation is a linear value. Okay. So that actually completes the proof of all the results. Okay. So we have successfully obtained from obtained the Lebesgue measure on RK using the Riemann, using the Ries representation. Okay. So our strategy was here quite different from what we used to do, what we used in the case k equal to 1. Okay. So that's a nice place where I think can stop this. So thank you very much, and we will meet again. Right.